So now I'm going to talk about an anti-forensics program called WinSlacker. It actually derives from an older program that used to come with Metasploit. It might still come with Metasploit called Slacker. And the Metasploit program was meant for an older version of NTFS. Actually, it worked on Windows XP, but stopped working when it came to Vista. So I took and reworked it pretty significantly and came up with a Windows version. And Derek Greenspan has created a Linux version called LinSlacker. Unfortunately, there's not much cross-code between WinSlacker and LinSlacker. And the reason for that is because both programs rely so much on the operating system API that there's a lot of very specific code. So right now, the programs don't share a lot of code. They're early in the development cycle, so at a certain point I might be able to create a single code base with a lot of if-defs. But for right now, they're two separate projects. But WinSlacker is an open source program that can hide and retrieve data from the slack space of a file. Now, you hear slack space, but I refer to two different types of slack space. In this case, I'm referring to the slack space of a file, and we'll see an illustration shortly. That's the part of the last cluster of a file where data was not written to. Now, this used to actually be called RAM slack, and that's because operating systems used to actually write the last cluster in its entirety based on whatever garbage happened to be in RAM. So a lot of times you'd get these miscellaneous things at the end of the cluster that had nothing to do with the actual file itself. They just happened to be found in RAM. Well, that's long ago been stopped. So there really is no such thing as RAM slack. I just refer to it as file slack. Now the other type of slack is disk slack. Disk slack is unallocated disk space. So let's say I find a place on the disk and it's completely unallocated, and I can just read and write to and from that area. The only thing is there's a tremendous danger that it gets overwritten. With file slack space, let's say you optimize or defrag the disk or move a file around, it's actually normally pretty safe. And it's very difficult to detect, although there are lots of programs that do it. FTK, Autopsy, WinHex can help you, but under normal circumstances it's going to go undetected. But anyway, slack space is the unused space at the end of an allocated cluster. Actually, it's always going to be the last cluster in a file. NTFS allocates an entire cluster even for small files. And I really need to kind of amend that. So there are really, in NTFS and Windows, there are really small files that will not allocate even a single cluster. These will become what are known as resident files. And from my experimentation, which is not based on any kind of research because I can't find it, but I just did a lot of experimentation one day. I basically chewed up hours doing this. And I found that 168 bytes and less would get saved as a resident file. That may have changed now with Windows 8 and Windows 10, but that was, so anyway, don't get hung up on that value of 168 bytes, but there is some cutoff point where it will be a resident file and it won't allocate a cluster. So clusters are normally 8 sectors, each of which have 512 bytes for a total of 4,096 bytes for the cluster. Now, this actually can be adjusted by the operating system. The operating system can go in and, now it has to do it for the entire drive, it can't just do it for a single file. But I just want to point out that these are the normal values. You could always encounter some operating system disk that isn't observing these normal values. So for that reason, you always need to query the operating system and find out the disk parameters. And I will show you that in WinSlacker and how I got those parameters, because you never want to hard code these values. So here's the topography of a cluster. Notice there are 8 sectors. Each of these sectors has 512 bytes, and grouped together it's going to be a single cluster for 4,096 bytes. And this is the normal way that these clusters are allocated. And in Linux, this is actually known as a block, not a cluster. So this illustration shows that you have a single cluster and you have a little bit more than 2 sectors that are occupied with written data, that is file data that was written to the disk on behalf of the file. Okay, so where it says data in the blue color, that's the actual file data. And you'll notice that you have all that slack space to the right of it that's in the magenta color. And so that's 1, 2, 3, 4, 5, say 5 3/4 sectors. Now, I took a conservative approach for WinSlacker, and I did not write to any partial sectors. So WinSlacker is only going to write to the last 5 sectors of the slack space, in this case, or less even. It depends on the situation. But WinSlacker doesn't write to partial sectors just for safety and conservatism. So here we are at the WinSlacker code. And I just wanted to say I'm in the process of writing an article about WinSlacker, really about slack space and how to write into it and read from it. So that should be done by the end of the semester, maybe by midsummer, but somewhere along the way I'll get that done. And like I said, I'm glad to send you this code. It's definitely far from being ready for public consumption. And as an example of that, I've only got one source code module here. It needs to be split up into multiple source code modules, but you know, at the moment, I just got it done and just wanted to make sure it was working. So here we have everything in main. It's just looking for whether to embed or to extract. Okay, and the usage is pretty simple. You either embed, and this is a carrier file, which hopefully has some sort of slack space at the end, and it will tell you if there's not enough room. And at some point, I'm going to write a utility that creates a carrier file so that you can create a carrier file with maximum slack space. Anyway, and here's extract. Okay, so this actually loads the message data from whatever the message file or payload file happens to be. It's really pretty simple. It does a lot of stuff though, because what it's going to do is it's not going to write the exact number of bytes. It's going to actually write the bytes on a multiple of 512, or a multiple of whatever the bytes per sector is. Here, I didn't hard code it like I told you not to. Whatever. So I found that it works a lot better if you write even multiples of bytes per sector. Okay. The first 5 digits actually of the stored data are the length. So what I do is I use a sprintf to actually create the data string, and that's so when you read in the data, you know exactly how long the payload is. Get file length is this is a cross-platform function that if you were on Windows, it would be that underscore file length file no, but that's not available in the GNU-C for Windows. And a lot of this, starting here, is all API calls. This is actually where I get the disk parameters: sectors per cluster, bytes per sector, free clusters, total clusters. So these two parameters are what I need from the operating system in order to make sure I'm not hard coding any kind of values. But most of this is actually a lot of API call. Get file system format. I need to know if this is NTFS or FAT32, because at a certain point I have to actually adjust the starting point of the data. And here's where I actually adjust for FAT32. FAT32, the starting cluster of the root directory, is logical, while in NTFS it's physical. So you actually have to read the boot sector in FAT32, and you actually have to generate the offset and what you need to add to the extents. So here I've already got a list of all clusters, and I just adjust it by adding that value that I determined from FAT32. So here's where I create a cluster map. This is basically all Windows API code, pretty much. And it's totally different on Linux. So at a certain point, I'm going to go ahead and write something up to explain all this. But basically what I'm doing here is creating the cluster list from the extents. Okay, and this is just setup stuff. And here's where I actually do the embed. Check for enough arguments. Set up my values. Okay, so you cannot hide into a Windows system disk. Like C, if your system disk is C, you can't write a sector there because of security reasons. Now, at a certain point, I wrote a device driver that then allowed me to do this. But what happened was the device driver wasn't signed, and there's no way in the world they're gonna sign it for me, knowing what it's for. So every time my operating system would load up, I'd have to give permission for the device driver to load, which is okay since it was my system and I knew what it was for. But on some sort of suspect's computer, you're not going to be able to get away with that. So I just gave up the whole idea of hiding to the system disk. And just bear in mind, it is possible, but not without a system driver. Okay, load the message data, create the cluster map, which I already showed you the code for, and that automatically adjusts for FAT32 if there's FAT32. Now we check to make sure there's enough space. Tell the user, set up the disk access values, and this is the Windows way of actually opening the disk. And I've been testing this to USB devices, both FAT32 and NTFS. So we seek to the correct point. And the interesting thing about Windows, we actually have to lock the volume, or on some systems it won't correctly work. So it's a weird Windows thing. Like I said, a lot of this is straight API code. Okay. So here I go and write a sector, and I write sectors until I'm done, and I unlock the device, and I close the disk, and I free everything up. So now here's where we extract. Extracting is actually a bit easier. I do the same setup stuff. I still have to open the device, seek to the correct place, and I don't have to lock the device when I read. Okay, so I read the data, read the first sector, and then I actually loop through the rest of the sectors. The reason I do this differently, I read a single sector so I can actually get the size. Remember I said I take the first 5 bytes and that they're an ASCII representation of the size. So anyway, that's it. Some support stuff, but that's WinSlacker. Okay, so here's Derek's version of WinSlacker, and he actually gives UCF credit, Wendy credit, himself and me, so that's the kind of stuff I need to do for the WinSlacker version. He does all the typical argc, argv stuff just to make sure everything's cool. And this is his way of actually getting the file information about the disk. Okay, so here again, he's not hard coding stuff. He's actually getting the disk information. So here, write data, read data. And that's it for main. And so here's his file system code. Gets the number of blocks, unused sectors. He's getting stat information, block size, block count, and the file. And since it's a large number, he uses an unsigned 64-bit integer. So I can't describe this too much, but you can see it's pretty straightforward code. So at a certain point, I'm going to also be able to post this too. What I'm going to do before I even do that, I'm going to try to create these so that they have more. Both code bases are more similar. I'm going to actually see if I can do the miracle and create a single common code base.